Right, hello and welcome back to another video. Today we're going to be continuing with our explorations of Niagara, and we're going to be having a look at GPU particles, vector fields, and some collisions and collision events. So quite a lot to get through, so let's get started. So just going to start a new system from a template, and I'm going to start with the, not from a template, from an inherited emitter. Here we are, and I'm going to start with this fountain. Let's put that into a new system I'm going to call GPU. So with Cascade, you had the option to add a GPU emitter. With Niagara, things are slightly different in that any one of your systems you can tell here in emitter properties to use a GPU compute sim instead of a CPU sim. So what does that mean? Well, that means that the calculations doing the particle system, working out locations, all those kinds of things, will be done on the GPU instead of the CPU. And there's a few advantages to this and some disadvantages, and we'll go over those now. But we want to sort of quickly explain what the hierarchy or the system of how a computer sort of processes things. So if I go to here, you have two threads. There's two kind of thinking parts to your computer. CPU's doing all the calculations, this is sort of the brain, and then the GPU's doing all the drawing. This is like the arm, I guess, in that example. And it's a one-way street, so you can only send data from the CPU to the GPU. You can't ever get it back. GPU is very optimized for lots of parallel calculations, so shaders, all that kind of stuff. Really good at that, but it's not going to then pass that information back to the CPU, because in this case the CPU is already thinking about the next frame, sort of calculating the draw calls, doing the AI, all that kind of stuff. So it's a one-way system. So in Cascade there was a number of things you couldn't do with the GPU emitter. So you couldn't affect things like acceleration over time, because that involved kind of like a back and forth between the two systems. Niagara's been rewritten from the ground up, and now you can do a lot more on both CPU and GPU, and so it's a bit more flexible than the old Cascade system. But there's still some things, and when we get to collision events, that's something that requires the GPU to know when the collision has happened, and so that can't be done on the GPU. So there are still reasons to do both. And talking about performance, one of the reasons you might want to move things onto your GPU, it's a lot faster, and it depends what your kind of performance bounds are. So if I just go into my scene here, I'm just going to load up a couple of stat commands. So firstly, stat FPS. Oh, apparently I'm not in my console. So the console command is tilde, which is the little button next to 1 on your keypad, and I'm just going to do stat FPS, give me my frame rate, and I'm going to do another one which is stat unit, and what that's going to give me is a breakdown, let's move that's a bit easier to see, of the different threads. So here my total frame is taking 23 milliseconds, which results in a frame rate of about 45 frames in a second. But you can see my GPU is the thing that's taking 23 milliseconds, and I've got my game thread and my draw thread. So game thread is doing all your sort of physics and AI, game logic, and then the draw thread is the CPU telling the GPU what should be being drawn. Maybe slightly simplifying this, but this is sort of my understanding of these things. So in our case, we've got very little things in our scene, so our draw thread's very low, but our GPU is the thing that's taking the most time, and the total frame time will be whichever of these is the highest value, because that's the thing that's causing your bottleneck, that's the thing that's causing the most. So in this case, our GPU is the most expensive thing. We're what's called GPU bound, so we wouldn't want to move our simulations onto the GPU unless we had a reason to do so. If you're CPU bound, it might be possible to then move some of your simulations to the GPU, and that'll move the costs and help free up some resources. So ideally you want to use these things as equally as possible, but obviously it's never possible to get things sort of perfect, and games are very variable and different frames change and all that. So that's a bit of an understanding about what these things are doing. So I'm going to do something really bad now and totally kill my frame rate. So here we've got a let's bring one in scene. Here we have our particle system that is on the CPU. And if I just up my spawn rate, so I'm just going to turn on the particle counts. Now, I've got a pretty powerful rig. If I start spawning 10,000 particles a frame, you see I have an 18,000 particle count here. It doesn't really affect my frame rate too much, so I'm just going to keep cranking these numbers up until things start getting bad. So here, getting down to 26, 27 particles a second, frames a second, and that's with 100,000 particles a second. Let me just try 500,000. Don't want to kill my recording too much, but that seems to be okay. So now we've totally killed our frame rate. We're spawning horrific numbers of particles, and it's really struggling because it's doing a lot of calculations, and you can see it's all calculating on our game thread. Well, if I go to my emitter properties and change this from CPU to GPU, it's going to give me a couple of errors. I'll go over those in a minute, but the noticeable thing is my frame rate comes right back. So one of the big differences with GPU particles is they're very, very efficient. Like I say, GPU's pretty good at lots of multiple parallel threads. And say I've got a pretty good graphics card in here, and so we can get here, what's this, nearly a million, sorry. So we've got 900 something thousand particles, yeah, capping out at 1.06 million. But if I put this back to CPU, obviously my frame rate goes absolutely into the tank. So if you're doing something that has a lot of little points, obviously GPU is going to be much more efficient if that thread is the thing that's you've got some performance to use on. So let's just put that down to something a bit more manageable. It doesn't actually look very good. There we go. And then we'll go over these errors. So a couple of errors. First thing it pops up here is it's actually a warning rather than an error, saying that we're using a GPU compute sim, but we don't have any fixed bounds. So I've talked about bounds before. I have a video about bounds when talking about this with Cascade, but same things apply here. The CPU doesn't know where the GPU particles are, so everything's being calculated on the GPU, so the bounds of the object, how big it is on screen, aren't being updated. If I go put this back to CPU, you can see here the bounds, which I've just enabled here. You can see how big that is, and it's updating. You see as the particles spawn and die, and that's something the CPU can calculate for us to make sure that everything is on screen when we need it to be. Well, if I change this to be a GPU simulation, suddenly our bounds are not updating, and if I move my camera, you can see we get this pop as the object bounds. The engine thinks the object's off screen because the bounds are off screen, but actually the particles are still visible, and so we're getting this popping. So we need to set a fixed bounds, and we can go in and measure this, or if we click this little down arrow, there's actually an option to set a fixed bounds, and it'll just take the extremes that you currently have and set that for us. So a little warning that we need to kind of fix, and then if we recompile, it'll tell us that warning's gone away, which is great. So a couple of little things that we have to use for GPU. Now, one of the reasons that we would use GPU particles in Cascade is we could use vector fields, and that's not true anymore. We can use vector fields now for either CPU or GPU, and I'll just do a quick demo of what they are. So in Maya we have a vector field, so we're not going to go over how to make one. I might do that in a future lesson, but this is just a 3D fluid, and we have a simple vortex, and we're getting this velocity. These velocity arrows, hopefully you can see, is sort of going around in a spiral, and this is quite complex motion. It's quite difficult to do with a particle because you'd have to keyframe its velocity going around over time, and really simple to do here and import, and so we can do that. So I've just imported that one in here, and I'll use the same particle emitter. So as I said, this used to be something that was only available on GPU particles. Now it's available on CPU and GPU. And we're going to do what's sample a vector field. Needs to be in the right place, needs to have an apply, needs to have the actual vector field thing loaded in. Now a vector field can be applied in two ways. Either we can apply it as a force, in which case a particle will take the vector that's at that point in the field and sort of adjust its velocity based on it being applied as a force, or it can be overwritten. So you can apply it as a velocity, in which case the particle's velocity is being overwritten by the velocity in the vector field. So if I just go in here and set this up, you can see now we're affecting that velocity with other things. You can see that swell coming through. Probably is the wrong orientation. Unfortunately, there is a axis issue with the vector field exporter that Epic provides. So again, we'll do all this in another lesson, but no, not that one. Vector grid explorer. So there is a vector grid exporter. Comes with the engine, but unfortunately it gets its axis wrong. So we probably just need to rotate this by 90 degrees. Maybe not. Is this 90 or is this 0.5? Looks like a 0.5. So let's tile this. And you can see we're getting some quite complex motions. Must be 0.5. Quite complex motions from that vector field. Not as useful or not as necessary as it used to be. Again, Niagara's added some quite nice new things, one of which is things like curl noise, which kind of takes into account that that non-linear motion, and so now we can use a curl noise force to create some sort of turbulent style motion instead of am I not getting any curl noise? There we are. And turn off some gravity as well. Maybe get some, and then we can see the curl noise coming in. So that non-linear motion that we used to use vector fields for, we can now do with curl noise instead. So really useful, really powerful. Not limited to GPU particles anymore. Can now be used on CPU particles as well, which is nice sort of little feature to have. So where might we want to have CPU particles? What features can't we use with GPU? And that's with collision events. So I'm just going to create just reset this back, turn off my curl noise, have my gravity and my velocity, and I'm going to add a collision. So again, I'm on a GPU compute sim here. If I go in here and type in collision, it needs to be in the right place. We'll click fix, and that should fix that for us. And then if I type in generate collision event, it should give me a warning. It doesn't. Okay. Okay, well, we'll try this. Oh, there we go. Just had to recompile. Cannot use event write on GPU sims. So you can't generate collision events on a GPU simulation. So that's, as far as I'm aware, or at least the only limitation that I've found so far. And that's what we want to use in this example. So I'm going to put this back to being a CPU sim. And if I click recompile, it's going to give me some errors. What's the error? Down here. We cannot, or before particle ID parameter can be used, requires persistent IDs option to be activated in the emitter. And it gives me the rest of the warning, says this will come with additional memory and CPU costs. So you don't want to just turn this on. But what is that? Well, in the emitter properties, we have this option here, requires persistent IDs. So this is something under the hood that is required. Basically, each particle will have a number, and that will be unique to it, and it will be persistent all the way through, and that's required to generate collision events. So what are we doing with collision events? So what's happening now? If I go back to the world, you can see we've got particle collision happening. So these particles are hitting the ground, and we're getting a collision, and I want to create a quick burst effect when they collide. I'm just going to lower my spawn rate down because I don't want to go crazy. There we go. So I need another emitter to sort of receive the spawn. So this is creating a collision, and we're getting the bounce, and we're getting a collision event. So we're getting some information about where that collision happens, and velocity and things like that. And we need now something to receive it. So I've got just a simple burst emitter from previous examples. So I'm just going to add that Niagara burst effect. And if I just isolate it, the little man on his own symbol, we can see we're getting that burst. Let's turn this bound off. We're getting that burst of particles. So I don't want to spawn any with the emitter on its own. I just want to spawn on the collision event. And the way we do that is by adding things to the event handler. So this, try and get my UI so I can see what's going on. This is where we tell it to spawn, to listen for the event. So we need a source. So what's the source? Well, it's the fountain collision event. And then the execution mode, we want this to just run on spawned particles, not on every particle. I'm not 100% sure why. It doesn't work on every particle. That feels like spawned particle should be a subset of every particle, but this seems to be the thing that we need. So not quite working yet. We seem to be getting a bit of a burst happening here, and then the whole thing just sort of stops. This took me a little while to work out what's going on there. Well, this burst emitter, if we have a look at its settings, it set loop behavior to once. So when we made this burst, we wanted it to just be sort of a single burst out in time, fire and forget, spawn particles, done. But in this case, we want the emitter to always be looping, and then the event to tell it when to spawn. And so we need to change this loop behavior to infinite. And now this particle system's always running, and we see we're getting our bursts happening, but they're happening in the wrong place. They're not happening at the collision location. And why is that? Well, we haven't passed that information through. So we've got a generate collision event, but we don't have a receive collision event. And now, if I've done this correctly, as the particle spawns and hits the ground, the event handler, let's put that down a little bit, it's the collision event is happening, the generate collision event is taking that data, and then the receive collision event is receiving that data, and we're getting this happening where we get our little kind of secondary bursts as those particles hit the ground, which is pretty cool. If I put this to every particle, it's now triggering on the particles that are spawning as well as the particles that are doing the collision, if that makes sense. So as far as my understanding of this, now the particles that are being spawned by the collision are also then colliding and bursting, so we're getting this kind of weird result here. So if we just set this to spawned, this gives us the sort of the result that we want. So yes, I think that's everything for today. Quite a lot of little topics, GPU and CPU emitters. Can I change this to a GPU and have event receive? Looks like maybe. GPU event scripts are currently unsupported. Okay, so nope, can't do that. So where we might want to, well, where we are forced to use CPU sims is when we're using collision events. There's also death events, and what other events are there? I believe there's another type of event. It's not in that one, is it? Delete this. Just type in event. Location. So you've got three types of event here. If we're using those events, we need to use CPU emitters because we need the calculations to know where they are at all points. If we're not using collisions or collision events or events in general, then we should be able to just put everything on the GPU if we need to. It doesn't necessarily make things better. It depends where our bounds are, what is the thing that's currently most expensive. On a lot of games that I've worked on, you are GPU bound, so moving things onto the GPU isn't necessarily a good thing unless you need it for some reason, and the only reason you might need it is if you're using a lot of particles. So a few thousand particles, what we've got here, isn't making a huge dent in our performance, depending on obviously target hardware and everything like that. But once you get into the hundreds of thousands, you definitely want to get onto the GPU for performance reasons. So yeah, hope that was interesting and helpful. We've got a couple more videos in the Niagara series, and if you have any questions, let me know. Big thanks to my patrons for supporting the channel, and I'll see you all next time.